Welcome to the video lecture on Shannon Fano Encoding. Shannon Fano Encoding is one of the source coding methods used to encode messages at the transmitter. It assigns binary zeros and ones for the messages or symbols with their probabilities of occurrence at the transmitter. Generates variable length code to give lowest possible values of average code word length. Since it provides maximum efficiency, it is also known as optimum code or minimum redundancy code. So now we'll see the algorithm employed in Shannon Fano encoding. Step 1. Arrange the messages or symbols in the decreasing order of their probabilities. Step 2. Partition the entire set of probabilities into two sets that are equiprobable or as close as equiprobable. Assign a binary 0 to the upper partition set and a binary 1 to the lower partition set. These partitions are further divided into new partitions based on the above said rule. The partitioning is stopped when there is only a single message in the set. Finally, we can calculate the efficiency. So with an example, we'll see how to apply Shannon Fano encoding. So problem what I've considered is apply Shannon Fano encoding for the given messages with their probabilities and calculate its average code word length and its efficiency. So the messages are from x1 to x7 with the probabilities as given. So the first step states arrange these messages in the decreasing order of their probabilities. So now message x6 is having the maximum probability 0.3 followed by x7 with the probability of 0.25, x5 with the probability of 0.20 followed by x4 with the probability of 0.12, x1 with the probability of 0.05. Now consider the message x2 and x3. They are having the same probability 0.04. We can either place x2 followed by x3 or x3 followed by x2. Both are correct. So Shannon Fano code is not a unique code. Now I have placed x2 followed by x3 with the probability 0.04. The second step states the entire set of probability has to be divided into two sets such that they are equiprobable. This we can achieve only by trial basis. Since we know it is arranged in descending order, the top probability will be having the maximum value. So first try, I am going to consider 0.3 in one set. So the value is 0.3. And the remaining probabilities in the second set, the sum of the probabilities is 0.7. The difference in this case is 0.4. The second try what I am going to consider is, I'll consider 0.3 and 0.25 in one set. The sum of these two probabilities are 0.55. And the remaining probabilities in the second set, the sum of these probabilities are 0.45. The difference in this case is 0.10. So the second trial is better compared to the first one. So I'll go for the partition here and I'll assign a binary 0 to the upper partition set and a binary 1 to the lower partition set. Now in stage 2, we are supposed to consider upper partition set separately and lower partition set separately. In the upper partition set, I have only two values. So I can go for the partition in the middle, assign a binary 0 to the above portion and binary 1 to the lower portion. Now coming to the lower partition set, again go for the trial basis. So first try, I'm just going to consider 0.20 in one set and the remaining probabilities in the next set. The sum of the probabilities are 0.25. The difference between these two sets are 0.05. The next trial, I am going to combine 0.20 and 0.12 in one set and the sum is 0.32. The remaining probabilities in the other set, the sum is 0.13. The difference between these two sets are 0.19. So the first trial was better, so we can go for the partition here. And now assign a binary 0 to the upper portion and assign a binary 1 to the lower portion. Moving to the stage 3 and applying the partition in the similar manner, we can go for partition here. Assign a binary 0 to the above and binary 1 to the lower portion. Now stage 4, again applying the partition. So assign a binary 0 to the above and binary 1 to the lower portion. Now in stage 5, we have only x2 and x3. I can go for the partition in the middle, assign a binary 0 to the upper and assign a binary 1 to the lower partition set. Now almost all the sets are having only one value. We can stop the procedure at this stage. We can obtain code word. So consider the message x6 with the probability 0.3. The values which are assigned during the procedure is 0, 0. That is the code word. Similarly, for x7, we have assigned 0, 1. That is the code word. For x5, it is 1, 0. x4, we have assigned 1, 1, 0. That is the code word. x1, it is 1, 1, 1, 0. x2 with the probability of 0.04, we have assigned 1, 1, 1, 1, 0. And x3, it is 1, 1, 1, 1, 1. In order to calculate average code word length, we can form a table. So in the table, first column, consider the messages. Second column, consider the respective probabilities. Third column, write the code word. So we know for x6, the code word is 00. x7, it is 01. x5, it is 10. x4, it is 110. x1, it is 1110. x2, it is 11110. x3, it is 11111. The next column, we can find the length of the code word, that is LK. It's nothing but the total number of bits available in the code word. For 00, we have only 2 bits, hence the length is 2. 01, again we have only 2 bits, hence LK is 2. 10, we have 2 bits, LK is 2. 110, we have 3 bits, so LK value will be 3. 1110, we have 4 bits, LK is equal to 4. 11110, we have 5 bits. 11111, again we have 5 bits, hence the value of LK is 5. The next column, just multiply PK with LK, that is the probability of occurrence with the length of the code word. So 0.3 into 2, it is 0.6. 0.25 into 2, it is 0.5. 0.20 into 2, it is 0.4. 0.12 into 3, it is 0.36. 0.05 into 4, it is 0.20. 0.04 into 5, it is 0.20. 0.04 into 5, it is 0.20. The sum of all this will give average code word length. So we know L bar is equal to summation k equal to 1 to m pk lk. So once I add all the values of pk lk, I'll be getting 2.46. Now we can calculate the entropy for the given probabilities. So we know entropy is given as summation k equal to 1 to m pk log of 1 by pk to base 2. The value of m here is 7. So just removing the summation and substituting all the probabilities, that is 0.05 log of 1 by 0.05 to base 2 plus 2 into 0.04 log of 1 by 0.04 to base 2 plus 0.12 log of 1 by 0.12 to base 2 plus 0.20 log of 1 by 0.20 to base 2 plus 0.3 log of 1 by 0.3 to base 2 plus 0.25 log of 1 by 0.25 to base 2. We get the value of entropy as 2.411 bits per symbol. Finally, we can calculate the efficiency by the formula ratio of entropy by the average code word length. Substituting the values and simplifying, we get the efficiency as 98%. Thank you.